Okay, after an F test or an ANOVA test has been performed, and if the null hypothesis has been rejected, we can further investigate using a multiple comparisons test. The reason? We want to test for significant differences between the pairs. We don't remember the conclusion was we don't know if they're all different or two are different or more if we reject the null hypothesis. So what we can do is conduct a Tukey's HSD test. HSD stands for honestly significant difference. And the formula uses Q, which corresponds to the studentized range distribution with alpha, and the degrees of freedom are C, so the number of groups or treatments, and N subtract C, degrees of freedom. So we have a numerator degrees of freedom and a denominator degrees of freedom, just like we did with the F tables, right? The columns and the rows. Okay, and we multiply that value from the studentized range distribution by the mean square error divided by N, where N is the sample size for each for the groups. So if each group has the same number of observations, then you can use this if they're equal. Okay, so carrying on from the employee ages example at 3 different manufacturing plants, we calculated the average for the first plant, so the average age was equal to 28.2 years. The average age for the second manufacturing plant was 32 years. And the third manufacturing plant had an average age of employee for 24.8 years. Okay, so what we can do is look at each of those differences pairwise. The absolute difference, so 28.2 subtract 32 is going to be 3.8. Then we'll subtract the third one, the third group. That's going to be 28.2 subtract 24.8. It's going to be 3.4. And then finally, we want to know the difference between the second and the third group. It's going to be 32 subtract 24.8. Absolute value will be 7.2. We then calculate the HSD, so the Tukey test, and we can get our Q of, for this, we'll use 0.01 for alpha, and because there's 3 manufacturing plants, C is equal to 3, and N equal, there was 5 observations from each plant, so that's N equals 5, and so 5 times 3 is 15 total observations, so 15 employees. So that's going to be C equals 3, and then 15 subtract 3 is going to be 12, so that's 15 employees subtract 3 groups, 3 plants, will be 12. Multiplied by the MSE, mean square error, divided by 5 in this case, because there were 5 employees from each of the manufacturing plants. So we need to find the value for Q. So we'll go to our studentized table right here, and that is for alpha equals 0.05. For our test, we want 0.01, and we want to go to 3 degrees of freedom for the number of populations, and the degrees of freedom for the error was 15 subtract 3, so that would be 12, right? And that is going to give us a value of 15. I put here 12. We want 12. So it's going to be 5.05. Yeah, don't forget to subtract the number of groups. 15 was the total number of employees. Subtract 3 will be 12. degrees of freedom. So we use our Q is going to equal 5.05. We bring that over and just plug it in, 5.05. If you recall, the mean square error for this example in the previous video is 1.633, and we're going to divide by n. N in this case is 5. Carefully calculate that. Make sure all this stays inside the square root for your calculation. And I'm just going to get 2.89. So that is called our critical difference, 2.89. And what you want to do is compare the critical difference to each of these differences here. The actual differences. These are the actual differences because they come from the data. So 3.8 is greater than the HSD. This one here is greater than the HSD, which means they are statistically significantly different. And here, the last one. So this, we can conclude then that all pairs of means are statistically significant because they are all greater than the critical difference, the HSD value 2.89. Right, and that is how you conduct the Tukey's HSD test.